Hello, class. In this video, we're going to finish up section 2.5 on that solution by substitutions. The one that we were looking at last time briefly was this Bernoulli's equation in that format of dy over dx plus p of x times y is equal to f of x times y to the nth power. We said that was going to be a linear ordinary differential equation. And the substitution that we're going to use for this is to replace instead of this, u would be equal to y to the 1 minus nth power. So based on this example, x times dy over dx plus y is equal to x squared times y squared. We're going to divide by x. And this is going to give us dy over dx plus y over x is equal to x times y squared. So from that last equation, you had on that last slide for the substitution. And in this case, it's going to be 2. Why 2? It's because of this being a 2. So 2. So the substitution we're going to use here is going to be let u be equal to y to the negative first power, which is the same thing as saying if you let y be equal to u to the negative first power when we multiply by y and then divide by u to get that same aspect. And from what we know with regard to the chain rule, hopefully we'll spell that correctly, by the chain rule, we know that dy over dx is the same thing as dy over du times du over dx. So in our case, dy with respect to u is going to be negative u to the negative second power when we take that derivative, times the derivative of u with respect to x. So, applying this, we are going to get applying this, we're going to get negative u to the negative second power and then du over dx plus this would be 1 over x times u to the negative first power, and that'll be equal to x times u to the negative second power. So based upon this, we are going to divide by that negative u to the negative second power. So doing that is going to give us du over dx minus, this would be u to the negative first. So that'll be a u to the negative first minus negative 2. So that'll become u to the first power divided by x is equal to negative x. And now that definitely looks very linear. With what we had. So because of this, we're going to use an integrating factor. And this is going to be from 0 to infinity, but we don't want to include the 0 as our interval that this is going to be under. But this is going to be e to the integral of negative, and I should include parentheses for this, negative dx over x. There we go. And that is going to give us e to the negative natural log of x, which is e to the natural log of x to the negative first power, which, since the natural log and e cancel, this is x to the negative first power. And we're going to multiply our linear differential equation now by that x to the negative first power. So x to the negative first du over dx minus 1 over x squared times u would be equal to negative 1. That left-hand side is the product rule. So the derivative with respect to x, condensing it, it's going to make x to the negative first power times u is equal to negative 1. And we'll integrate both sides of this. We are integrating both sides of this with respect to x. So x to the negative first times u would be equal to, this is going to be negative x plus c. So to solve for that u, we're going to divide by that x to the negative first power. So this is the same thing then as u is equal to negative x squared plus c times x. But we had that substitution, right? So we need to reapply that. But u, from what we had from before, is equal to y to the negative first power, which means y is equal to 1 over u, or u to the negative first power. So what does that mean? That means y now would be equal to 1 over whatever u is, which in this case is negative x squared plus cx, as to what this differential equation becomes. We could also reduce to apply a separation of variables. So a differential equation of the format dy over dx is equal to f of ax plus by plus c can be reduced to an equation with separable variables using the substitution u is equal to ax plus by plus c. But in order for that to actually be the case, b in this case cannot be 0. Otherwise, we can't use this method. So, what does that mean? We want to solve dy over dx is equal to negative 2x plus y squared minus 7. And y of 0 is equal to 0. Per what we had from here, c in this case is equal to 0, which is fine. It's just b, that y term can't be 0. So because it's not, we could just follow through with this to actually get our solution, which this one uses that partial fractions that we previously talked about. But anyway, the substitution that we're going to use, and I'll start this up here since this one can get a little long. Let u be negative 2x plus y per our equation. So with that being said, the derivative of u with respect to x is going to be negative 2 plus dy over dx, which means from what we have here that du over dx plus 2, so just by adding that 2 over, is equal to dy over dx. But since we are using our substitution of u here, with our differential equation below, that this is going to make, and actually let me Let's move this over a little bit so I have enough room to write this instead of trying to squeeze it in such a small spot. Du over dx plus 2 is equal to dy over dx, which would be equal to u squared minus 7 inside of this case. And now that means that du over dx, I'm subtracting back over that 2 now, is going to be equal to u squared minus 9. And the separation of variable portion regarding that with this would be then divided by that u squared minus 9, multiplying by dx. So we would get, using that separation of variables, let me make note of that, separation of variables, we would get for this du divided by u squared minus 9 is going to be equal to dx. So we can't just simply integrate here. We would need to use partial fractions, which we've seen earlier. So I will not bore you with me going through that process of this one, but it uses that same method. So that du over u squared minus 9 we could factor that denominator. Du over, this would be u plus 3 times u minus 3. And applying that partial fraction algorithm involving this, again, the same exact way we previously did, would give us 1/6 times 1 over u minus 3 minus 1 over u plus 3. So based upon that, we could substitute that back into a separable differential equation. And this is going to make 1/6 times 1 over u minus 3 minus 1 over u plus 3. And then this would be du is equal to dx, which then means that we could then apply our integration involving this. So that would make 1/6 times the natural log of the absolute value of, we would have each one of these separate as in the natural log of the absolute value of u minus 3 minus the natural log of the absolute value of u plus 3, which we could then combine into one fraction as u minus 3 over u plus 3. And that would be equal to x plus some number, let's call it c sub 1, since we'll have to do a substitution involving this. So with that being said, we could, number one, multiply everything there by 6 to get the natural log of the absolute value of u minus 3 over u plus 3 is equal to 6x plus 6 times c sub 1, and then take e to the power of both sides of this equation. Left-hand side, thankfully reduces and whatnot to make just the this is going to combine here to make u minus 3 over u plus 3 is equal to due to the raising 6c sub 1, e to the 6 times c sub 1 power. Getting rid of that absolute value bars allows that to be positive and negative. I'm going to replace that with a c times e to the 6th power. So, based upon that, we could then solve that now for u, just like we previously did. So, using that method of solving for u, so multiplying by u plus 3, distributing, getting all the u terms to the left, everything goes to the right, factor, divide, we should get u is equal to 3 times 1 plus c times e to the 6x divided by 1 minus c times e to the 6x. So reapplying the substitution, since we had u is equal to negative 2x plus y, so that means y would be equal to u plus 2x. And then we would have to subtract that back over. I should say add that back over. Subtract. Actually, I don't need to do that part. We will replace the u with negative 2x plus y, add over the 2x to get y is equal to 2x plus 3 times 1 plus c times e to the 6x divided by 1 minus c times e to the 6x. And we were given an initial condition of y of 0 is equal to 0. So, replacing everything, all those x's in there with zeros and whatnot, we get 0 plus, this would be 3 times 1 plus c divided by 1 minus c. Solving this is going to give us a value for c to be negative 1. So our particular solution is going to be y is equal to 2x plus 3 times 1 minus e to the 6x divided by 1 plus e to the 6x as that particular solution for this. So let me know if you have any questions or concerns. Thank you.